So we're going to expand our work with partial fractions into repeated linear factors. So our linear factor that we've been working with up to this point is the factor x minus r. And the power of that factor is 1 because it is a linear factor. It's a simple linear factor. And that's the terminology that we'll use when we move forward with something called repeated linear factors. And all that term means is that it's a linear factor raised to a power higher than 1. So we're going to modify our process to include partial fraction for each power of x minus r. So we'll just modify our process. So if we have, for example, a rational function that, let me grab a different ink, maybe that's what my problem is. Let's see. What really matters here is the denominator. So let's see, if I have something that looks like 6x over x squared times x plus 2 cubed. So if these were my factors in the denominator, these would be considered repeated linear factors. And how they would decompose is like this. We would decompose it into a over x for the first power of x plus b over x squared for the second power plus c over x plus 2 plus d over x plus 2 squared plus, I'm running out of space here, plus the fifth and final term would be e over x plus 3 cubed. So the amount of work increases obviously as the number of coefficients increase, but we modify the process to include a partial fraction for each power of x minus r up to and including, the final power. So we're modifying the process. You're going to include a factor for each power. So for each power of the factor, for each power of x minus r up to and including the last power. I'll just call it the mth power. Okay, if this would be m in this case, and m is 2 in that case. Okay, so let's try an example. I'm going to pause here and find one that I like. Hold on. Okay, here's a good example, and it's in the lecture, and we'll finish it tomorrow. But I just want to set it up. So if I want the integral of x minus 5 over x squared times the factor x plus 1, I could decompose this. So that's your denominator. And that's going to decompose into a over x, and then you're going to add each term up to and including the final power, which is x squared, and then the last factor is simply a simple linear factor of x plus 1. So that would be your decomposition, your partial fraction decomposition, and then you would go through your normal process. And I'll take it out a little bit further, right? We're going to multiply this whole thing through by x squared, x plus 1. And when you do that, you're left with x minus 5 up top, and you're left with a x plus 1. Right, that's your a coefficient. And b left with x plus 1, and then c has the coefficient x squared. Oop. Okay, so we'd have to try either of the two methods in order to solve this, but I think I'll just yield the 3 equations. I think that's easiest. And again, you're going to have to pick which one you want to do. So this is ax. Something's going on with my stylus. This isn't good. Ax squared plus ax plus bx plus b, and then cx squared. Collect your terms. A plus c x squared plus a plus b x plus b. Okay, so equating these is pretty straightforward. You're going to get, and this is 0x squared. Right, so a plus c is equal to 0. It's going to yield 3 equations. A plus 3 is equal to 0. A plus b is equal to 1. And b is equal to negative 5. And we're lucky there. So we can go about and substitute in. A plus b, since b is equal to negative 5. A plus negative 5 is equal to 1. So a is equal to 6. Which would put a plus c is equal to 0 is the same thing as saying, do it this way. It's the same thing as saying c is equal to negative a. And we know that a is 6, so c is equal to negative 6. So this integral becomes 6 over x, negative 5 over x squared, negative 6 over x plus 1 dx, which is a lot easier to integrate. And you're left with 6 ln of x plus 5x, oops, plus 5x minus 6 ln of x plus 1 plus a constant. And that's your answer using the integration by parts method. Okay, I'm going to pause there and one last concept. Okay, for our last concept, we need one more vocab word, and you already have a feel for this, and that's irreducible. Let me grab another color here. So if a irreducible, so all that irreducible means is that a polynomial can't be factored further over the real numbers. So it's irreducible, it cannot be factored further. Okay, so you can't factor any further. You're simplified. You can easily check whether a quadratic is irreducible. And that's pretty primarily what we're going to be looking at is quadratics. We're not going to go beyond that. It's beyond the scope of doing things by hand. So if we look at simply quadratics, to determine whether a quadratic is irreducible is pretty simple. You just look at the discriminant. So quadratics are irreducible if the discriminant, I recall your quadratic formula, okay? So if your discriminant is negative, then you have an irreducible quadratic, and I'll show you how to deal with that. Right? So let's look at an example where we can see all four types of factors. So far we have a linear factor, and we just went through a repeated linear, and now we know that there's something called an irreducible quadratic. And then to complicate things, we have repeated irreducibles. I'm going to have to page right. Okay. So let's use the same process that we've always done, but when we factor and run into a simple irreducible quadratic factor, we have to use a different term. So we're going to use the same process. This is really frustrating. We're going to use the same process, but when we factor, and run into a simple irreducible, we're going to use the term ax plus b in the numerator over whatever the quadratic is. I'm going to pause here and we'll look at an example. Okay, so here's our example. It's also in the PowerPoint. It's example exercise 2 in the PowerPoint. And looking at the denominator, the first quadratic we can actually factor. The discriminant is positive. The second quadratic is has a negative discriminant, so it's actually finished. It's an irreducible. So this is an irreducible. And the other one we have to factor. So let's go ahead and do that. This factors the leftmost quadratic. Factors into x minus 4 squared. And then this is the irreducible quadratic. That's just going to stay the same. So the partial decomposition is going to be a over x minus 4 plus b over x minus 4 squared, right, because that's a repeated linear factor. And then the last one is a irreducible quadratic, so it's going to be 6x plus d all over the irreducible. I'm not going to work the integral or anything. This is just the partial decomposition. And that's how the irreducibles work. I think that's it for tonight. We will resume this tomorrow with some problems.